Swayam Prabha. Digital India. Educated India.
Good morning. Today we are going to see the important application of finite elements, that is to the field of solid mechanics. So this is the most popular application, and you see extensive work has been done in this one. And of course, there are other cases like heat conduction and all that are also there, but the main application is solid mechanics. So in solid mechanics, it can do a host of problems, many problems that's related to solid mechanics. But we limit ourselves to the elastically deformable solids with linear elastic properties. So that means that we are limiting ourselves to the linear problems. And that too, for the moment to start with, we do the static case. Maybe if the time permits, we'll go for the dynamic case. And of course, finite elements is quite powerful. It can do many other things, many other materials. Non-linear materials like plasticity, viscoelasticity, viscoplasticity. And also it can do many other things like large deformations. Many non-linear problems, it's capable of doing it. There are lots of applications in that area also. But for the basic course now, we will introduce you to the linear elastic solid mechanics. And then that, of course, for small deformations where the linearity is there, and the strains and all that, they are first derivatives of the displacements. Okay, so the solid mechanics problems can be in many dimensions, either one-dimensional problem or two-dimensional problem or three-dimensional problem. And one-dimensional is a little simple. In fact, I have already introduced you to some extent in my early lectures, but we are going to put them all systematically here. And then we are also going to put down the 2D and 3D. 2D and 3D can be done together, or I will do it 2D and I'll explain 3D wherever it is necessary, wherever it can be extended to 3D also. So going from 2D to 3D is not that big a jump, but however, going from 1D to 2D is really a lot of issues are there. So to start with, let's look at the various equations that are to be considered while doing the solid mechanics. So let's look at, to start with, we have obviously the number of variables here. In 1D case, it is only axial deformation. We talk about 1D dots with the variable cross-section also. And in 2D, we have two variables, two displacements in x and y directions. We call them as u and v, which are functions of x, y. And then in 3 dimensions, we have 3 variables, u, v, and w. And obviously, the number of dimensions are x, y, z. So each u, v, and w are functions of x, y, z. So there are many examples which you can talk about. So in 1D, we have variable cross section, This is the x-axis, and we are going to consider only one-dimensional rod, probably with cross-section, thin cross-section here, which may be a function of x here. And then the variable of interest here is the displacement, u in the x direction, and which is a function of x means. So now it has a dimension in the other two dimensions, y and z, but we assume that the variation in yz across the cross section is negligible or is not there. And so what we mean by that is that if there is a cross section here, so every point in this cross section will have the same displacement u. Okay, so that's why we say that u is just shown as a function of x, and the displacement is in the x direction. So there's a cross section here which may be a function of x, and the materials obviously we depend upon Young's modulus, maybe a function of x. It's a composite rod if you want. And now let's look at the load that's acting here. One is it may be subjected to end load at x is equal to L, and there may be also a load here, distributed load all along the rod. So this is Q, which is a load here. Can be a function of x, and there can be an end load P. Okay, so these are, end load is the boundary condition, and what is the other boundary condition in this particular case is the boundary condition here. Well, I'll explain it a little later. So the governing equation here, which we have is derived, of course, last time we derived it. So there is so here making the equilibrium equation, so you have so this is the equilibrium of the load. So sigma x acting this way, sigma x plus delta x here in this on the cross section A plus delta A, and sigma x acting in the negative direction, sigma x times A and Q times delta x. So this is this we have derived earlier. So this is comes simply as sigma x delta A delta sigma x times A, and so here if you want we can write it in the limit. And knowing that sigma x is E times epsilon x, and du by dx. So this is, so we can write it as the governing equation d dx of AE u by dx plus q is equal to 0. So that's what d dx of AE. In fact, A, want A, you can put it inside, or we can also put it as delta A also here. Okay, so that is actually, it is slightly here. The total force here is sigma x plus A delta A, and then you can write it as one more term here. In fact, here we can write A plus delta A and delta of A times sigma x. Okay, if you want it to be more precise, we can also do it here. Let me just do it here. To be more precise, we can write it this way. Okay, so just to take the variation of A also, we have taken that into consideration here. So that's fine. So this is the governing equation. So this is valid anywhere between 0 to L. And then we also have the boundary conditions are, here the boundary conditions are u is equal to 0, at x is equal to 0. And on the right end, we have AE u by dx at x is equal to L should be equal to. Okay, so that means that the total force here on the cross section at x is equal to L should be equal to the applied load here. So this is okay. So these are the governing equation and the boundary conditions for 1D case. So we will come back to this one while developing the finite element equations. But let's also look at the equations, governing equations. For 2D and 3D. So for 2D and 3D, so we have several examples here. So 2D cases are, for example, a plate with a hole subjected to in-plane loading. So finding out the stress concentrations and all that straight away comes for 2D. And then 3D, so you have the many applications in mechanical engineering like piston, cylinder, or even the connecting rod. They are all of 3D solids subjected to loads which are in 3 directions. And then even the displacements are functions of x, y, z. So these are 3D applications. So here so if this is the body, and here, then this is the body omega, or sometimes we call it as volume. And then we have gamma here, the boundary. And so here, there are different variables of interest. So one is, of course, the stresses. So here, every point P here is subjected to the displacements. P undergoes deformation. So the displacements are U, V, and W, which are functions of x, y, z. So these are the primary variables in the sense that everything else can be converted into these variables. So these are, and then we are trying to find out the solution for u, v, and w, approximate solutions for u, v, and w. And so this is the basic primary variables. And now the governing equations at any point are in terms of differential equations of stresses. So the governing equations are in terms of differential equation, which are in terms of stresses. And are in terms of stresses. In terms of stresses here, of course, here the stresses are three-dimensional. And if you take so we have x, y, and so these are the basic directions. And if you take these stresses can be represented on a small, infinite small cube, and this sigma x and sigma xx or sometimes sigma x only. So this is the face called x, and this stress is called tau xy. So these are on the face x. This is called face x because its outer normal is in the x direction. So similarly here, so we have sigma yy, tau z, and okay. So these are the 9 stress components. There are 3 stresses on each face, and normal stress, and then the 2 shear stresses, sigma x, sigma xx, normal stress, and tau xy and tau xz. Tau xy is the shear stress in the y direction on the normal face x. So similarly, you have sigma yy and tau yx and tau yz, the shear stresses. Sigma z and tau zx and tau yz are the shear stresses. So these are the 9 stresses, but the independent quantities are only 6. So there is a symmetry or complementary shear stresses. The shear stresses here, tau yx and tau xy, are same, and so they are called complementary equation. And like that, so there are only 6 independent quantities, and the governing equations in terms of stresses are like this. So we have dou sigma x by dou x. So this sigma x, sigma y, sigma z are all functions of x, y. I will just explain what is this x bar is. So this sigma x can also be written as sigma xx to be more precise, in sigma yy and sigma zz. But as long as you understand that they are normal stresses, it is fine. And tau xy and tau ix, so we are taking them to be equal. So we are not really differentiating. Otherwise, they should have been written. So the probably to be more precise should be written as yx and zx. But in any case, so these are the three governing equation. Okay, so these are the most important three governing equations. So one thing right here, there are two things. This x bar, y bar, z bar are nothing but body forces. So x bar, y bar are body forces acting in x, y, z direction. So these body forces are distributed all over the body, all over the material. So they act at each and every point. So just like you have the force due to gravity, that is a weight. So weight will be acting at each and every point equal to the magnitude of rho times g. So that is the intensity. So this is the intensity of loading. Okay. So multiplied by the volume will actually give the force. Okay. So maybe body force intensity per unit volume. So that's one thing. The other thing here is that this is for 3 dimensions. And if you want to have it for 2 dimensions, say in the plane xy, so all these things, some of the force components or the stress components will drop down, and we will see those 2D cases just now. There are plane stress and plane stress, so we will just talk about that just in a few minutes. And now the primary variables are displacements, while the governing equations are given in terms of stresses. So the relationship between these two, so we have to introducing some more variables. So then we also have strains. So the strains are 6 components: epsilon x, okay, epsilon y, and epsilon z, and gamma y, gamma yz, and gamma zx. So these are strain components. So these are related to the displacements as dou u by dou x. Okay, so I'm writing down all these equations so that the whole set of equations are here, and we can go from one set of one equation to the other easily. So gamma xy is dou u by dou y. So these are the shear strain components. Okay, so the strains are now in terms of the derivatives of the displacements. So that means that the stresses are related to strains, and strains are now being expressed in terms of the displacements, right? And then what is the relationship between stresses and strains? So the relationship between stresses and strains. So we'll call upon the relationship between the material behavior, how it relates stresses and strains. So the material may behave elastically or plastically or viscoelastically or in a linear or non-linear. So that will determine the relationship. Okay. So these are called constitutive equations. So this will relate the stresses and strains. Okay. So for 3D, so we have epsilon x is related to sigma x by E. So the Poisson's ratio will come into the picture, and epsilon y is sigma y by E minus sigma x by E, and okay, where E is the Young's modulus, and we are assuming that isotropic material, but can be anisotropic also, orthotropic, in which case you can use Ex, Ey, Ez. Then the Poisson's ratio also will have the nu xy, nu yz, and nu zx. So that kind of nomenclature we have to bring in. But for the moment, so we are just using the isotropic material. Okay, so these are the three normal strain relationships. Apart from that, we have the shear stress and shear strain relationship, wherein the G is shear modulus. Okay, so you can also relate the G to Young's modulus as 2 into. Okay, so this is how the stresses and strains are related with E is Young's modulus, and mu is Poisson's ratio, and G is the shear modulus. Okay, so this is how we define the stress strain relationships. And now let's look at another important thing, is that after giving the governing equations, so we also need to give the boundary conditions. So that means that you have a body here, and on the boundary here, so it is possible at, so you support this, okay, and wherever you support this part of the boundary, so it can be boundary conditions or displacement defined. So that means that u can be defined as u bar, just like we are using the same thing. On the other hand, there are on some other part of the boundary, the forces or the tractions are defined. So then this is one type. So the traction is T here. So T is a vector here. Okay, it's a vector quantity. So T will have Tx, Ty and Tz. So this is defined, and these things are related to the variables here as, say, something like sigma x nx, tau ix and y, and tau zx and z is equal to tx. So what is this nx, ny and z? So these are nothing but, so you have outer normal here specified, and that normal has components nx, ny and z. So whenever Tx is defined, so that means that it is related to the stress components at that point by this relationship. So this all three will be there. So I'm just writing down all the three. Okay, all right. So this is the traction boundary conditions where Tx, Ty, Tz bar are defined and they're related to the stress components here. So that way, this is a complex interrelated variables. One is the primary variables are UVW, and while the governing equations, governing differential equation are given in terms of stresses. So these are the stresses, and so these stresses are related to the primary variables UVW through the constitutive equations related to epsilons, and epsilons are related to the displacement through derivatives. Okay, so, and while the governing equations are, the boundary conditions are, some of them are given in terms of displacement and some other may be given in terms of traction, so which are related to the stress. So it's all related, and so we gave 1D example very easily. Now let's give how all these equations can be taken care while developing the finite element equations. So that's what we are going to take it in the next lecture. So for the moment, it's bye.